Hello everyone, I'm going to record this tutorial on process optimization in HYSYS, and before I go into HYSYS and the problem that we are doing today, I just want to give you some background or the revision for process optimization. What is the process optimization? So optimization is the use of specific methods to determine the most cost effective and efficient solution to a problem or design of a process. So what are our objectives here? We want to have a cost effective method or the process, and we want to have an efficient solution to our problem. Now if you look on this chart, our optimization lies on the top of two things. One is the economical, which is the process economics, and other one is our production. And we want to maximize our production in order to have the optimization, and at the same time we want to maximize our profit and we want to minimize our cost. So if you have two variables, which is profit and the cost, they are related to the economics of the system, and if you have the productivity, that's what is related to your production. Now there are three recipes or the elements in a optimization: objective function, variables, and the constraint. So our main idea in optimization is we want to find out the values of the process variables that maximize. It could be your profit, it could be yield of the chemical reaction, or minimize. In minimization we can work on to minimize the cost, or we can work on to minimize the waste of the chemical plant. The objective function, which could be of two types, economic and or technical, I will explain to you in next slides. While satisfying the constraints, what are the constraints? These are the limitations within our process systems. So if I want to define you the objective function, this is basically a mathematical model that either needs to be maximized or minimized. So depending upon how you develop that model, we will go and see in the HYSYS about this. We will maximize our variable or we will minimize. It could be economic, related to the cost, profit of the production, or it could be a technical model. By technical, anything which is non-economic, it is counted as a technical aspect, such as the yield of a reactor. Now keep in mind, either economic or the technical, they both are linked to each other. If I give you an example, I would work on having a maximum yield, and alternatively I will be working on to increase my profit or decrease the cost. So this is why they both are linked to each other. We need to have the optimization in order to maximize our profit and reduce our production cost. It allows to allocate the resources, which are money, energy, at the time, in the best possible way to produce a cost effective product. It helps to attain improved and efficient design of a process. So that's what is your process optimization goals. So just keep in mind, whenever you are doing the optimization, at least one or more variables should have their values that we can change. If all the process design parameters are fixed, there is no optimization. So we must have at least one or the more variables so that we can vary its values and identify the best possible solution. Now let's do this in HYSYS, which is our workbook number 12 we did today in the class. So let me take you to the workbook 12. So this is our workbook 12 on optimization of a distillation column. So it is saying that 3700 kilogram per hour mixture of tetrahydrofurane, which is abbreviated as THF, and the toluene, which is present in which we have 44% mass percentage of THF at 100 degrees Celsius and 140 kilopascal is to be separated by distillation to get each of them with a purity of 99.5 mass percent of THF and 94 mass percent of toluene. THF is more volatile component. This means in the distillation we will receive more of the THF, and in the reboiler section we will have more of the toluene. So these are some column specification. We are required to find out what is the reflex ratio and the distillate rate. Along with these calculations, we also need to find out what is the profit associated with this system. We need to optimize this system in HYSYS. So this is the cost data. I will come back to them again when I'm using them in HYSYS. And this is my objective function here, which is the profit is equal to income minus cost, and income is divided into the income which we get by selling of toluene and by selling of THF as our products, and we subtract our cost. And now the cost is three types here. The first is our feed cost, the second is the heating cost, and the third one is our cooling cost. In this statement, use a range of 0.99 to 0.999 for THF and 0.9 to 0.99 for toluene. This is our limitation or constraint, just like I mentioned you in my power slides. So let's see how we optimize this system in HYSYS. The first step in HYSYS is always that we need to include our components here. So let's go to HYSYS and we will add up these components. I'm going to copy this component directly into HYSYS. So I'm in the component list in properties, click on add and just paste this one, or you can type in, this is my tetrahydrofuran. I will double click on this, and the next is my toluene, which is TOLUENE. So I have added two components. My fluid package, according to our statement, let's highlight the components that we have been using. So my fluid package is Wilson. We will be using that as the fluid package in this system. And I go to add for the fluid package, and here is the Wilson. HYSYS is okay with that, and now I can move into my simulation environment. I went to my simulation environment and go to the separator and bring in your distillation column into your solver. I double click on this, on the distillation column. Here I can define my streams. So this is my feed here, inlet. Let's say that for condenser I say it as a QC, and if you look on our statement here again, in the column specification, the condenser works on total condensation conditions. So I go back to my simulation, and out of these three options I choose my total condenser, and this stream, let's give it a name of overhead product. And for the reboiler, let's say I say it as a QR, and for the bottom liquid I say it as a bottom product. You can name them anything. So this is my bottom product. Another information is that my number of stages are 10 in my distillation column, and the feed enters at the fifth tray. So let's see and verify this information in HYSYS. So by default HYSYS has chosen 10 plates, and my inlet feed is entering at number 5. I can just double click and confirm this, so it is all good. Now I can move to my next step in column designing. Let's keep it as a regular HYSYS reboiler, and now we need to provide the condenser pressure and the reboiler pressure. This is available in your question statement. This is my statement for reboiler and condenser pressure. Condenser pressure is 103 kilopascal and the reboiler pressure is 107 kilopascal. So this is my 103 kilopascal is already there, and 107 kilopascal. If you have different units, you can always choose them from here. but for now it is my kilopascal here. Once you have entered your pressure, it will let you go next step, and we don't have these temperature information, these are optional by the way. Click on next. We don't have the reflux ratios, that's what we want to calculate, and click on done here. So let's go and provide our properties for the feed. So my feed is entering at 10 degrees Celsius. It has the pressure of 140 and it has 44 mass percentage of THF. This means the other component, because it's a binary mixture, the other component will be 56 mass percentage, and that will be for toluene. And I do have the mass flow rate given to us. So let's enter this information into the feed stream. So my temperature is 10 degrees Celsius, my pressure is 140 kilopascal, my flow rate is 3700, and I can go to my composition. For the feed, the THF composition is 0.44. So by default it comes as a mole fraction. You can also click on mass fraction, and then now we can enter our values here. And for other component it will be 56, of course, because both of them should be equal to 1. Sum of all fractions should be equal to 1 here. Just click on OK. Now we have defined our feed stream to our system. In the next step, we will go and provide these details. So we want to have a 99.5 mass percentage purity of THF, and we want to have 94% mass purity of the toluene. So how we provide this information? In your distillation column, just go to design and go to your monitor, and here we will add some more specification about our column. Click on add spec and select the column component fraction, because we want to include the fraction into our column. Click on add spec, and here we will write down. So let's say I give it a name of THF purity, and my stage for this one, because THF is more volatile as mentioned in the statement, it will go to condenser. I'm dealing with the mass fraction as I just showed you, and the value for this one, this mass fraction, is 99.5. So this will be 0.995, and I'm doing it for my THF, which is tetrahydrofuran. And now I can close this once I have defined all the parameters. As you can see that HYSYS has developed a stream which has a specification of the THF purity. The same procedure I will do for my next one, which is 94 mass percentage of toluene, but this time it will go to the reboiler. So click on add specs and click on component fraction, column component fraction, click on add specs, and now let's give it a name of toluene purity, and it will be related to your reboiler, and it will be the mass fraction, and according to my statement here, this should be 94 mass percentage, so that will be 0.94. and the components I'm going to work on is the toluene. And now I can close this. As you can see that I have entered two further information to my specification sheet of the distillation column. Now I want to include that into my analysis when the HYSYS run the simulation. How we include that and tell HYSYS to include them? Look at this active button here. You just need to click active next to your THF purity and click active on next to the toluene purity. Now by doing so, you can see that the degree of freedom is -2, The degree of freedom should be 0 in order to have the unique solution of our problem. So -2 means we have 2 additional component given to HYSYS. How we can make it 0? If you look on this specification, reflux ratio is something that we want to find out. As you see that the reflux ratio is something we need to find out, and the distillate rate. So I can uncheck this, and I can uncheck my distillate rate as well. And the time I did that, you can see that HYSYS has converged and it has performed all the design calculations for me. Let's close this, and this is my distillation unit. We need to do the optimization of this system. The next procedure which I'm going to explain you, this procedure is applied to every kind of the unit operations that you take in HYSYS for the optimization. Go to the Home tab and click on Optimizer here. Now in the optimizer, first we need to provide our constraints of the variables. So click on variables, and what are the constraints here? Now these are the constraints of our system. We must have some specification or in terms of the purity or the percentage compositions. So let's enter them in HYSYS. So in the optimizer, you go to the variable tab and click on add, and choose your distillation column. At this time it is T100 for me. You can name, you can have a different name if you have changed the name of the column. Click on the name of the column, and you can see that this is spec value. Click on the spec value, this small arrow, and it will drop you all the specifications that are being used in our system. So let's say I start with the THF purity. Click on this and click on select. What is happening here now? HYSYS, the optimizer in HYSYS, it bring the THF purity into this variable, and this is my current value, and these are the lower and the upper bounds which are selected by HYSYS. We can always change them. We will come back to that later. So let's add the next component, which was our toluene. So I click on add, go to your column, spec value, and this is toluene purity. Click on select here. So let's go back here. So my THF has a limit of this one 0.99 to 0.999. Now we will change this limit. This is 0.99 to 0.999 and hit enter. Now this is the value which is we have already provided, and the current value. What will happen, the HYSYS when it will run this optimization, it will change this specification from this lower value up to this maximum value in order to find an optimized or the maximum profit solution for us. The same thing we need to work on the next toluene. For the toluene, we have the limit of 0.9 to 0.99 to optimize our distillation unit. So let's enter this one. This is 0.9 and this is 0.99. So we have provided our constraints, which are categorized as adjusted variables in optimizer of HYSYS. The next step is we need to provide our input data. For that one, you need to click on the spreadsheet and go to spreadsheet. This is where we will do some calculations. So let's start and type some properties here. So my first is the condenser duty. The next is the reboiler duty. Overhead production rate. THF purity. Bottom production rate. And toluene purity, and the feed flow rate. So these are the variables in our study. In the column B, we will enter their values from HYSYS. So let's leave it blank and let's come to the column C. So corresponding to the condenser duty, I will have my cooling cost. Corresponding to reboiler duty, I will have my heating cost. And the THF purity, we do have the price for the pure THF price. And similarly for toluene, we have the price of the pure toluene price. And for the feed flow rate, we have the cost of the feed, so it will be the feed cost. And now we want to find out what is our profit here. So let's start to fill up the corresponding values in the column B and the D. First we will start with the column B. So I want to know what is my condenser duty. Right click this and click on add import variable. The duty condenser duty is in the stream QC. Click on QC and click on your power here and click on add. It will bring in this condenser duty into the system and click on done here. The next step is we need to provide the reboiler duty. Right click on this. I know that my reboiler, I gave it a name of the stream QR. Same procedure, choose the power, add this and click on done. In terms of the overhead production rate, that will be your mass flow of the overhead. Right click this, add import, and this is my overhead product rate. And over here we need to add the mass flow. You can either search here or you can type in, it's the same. So this is my mass flow and click on done here. For the THF purity, again right click here, click on add. Now the THF is something that I can find in my overhead product, not at the bottom. So I will go with the overhead product. It will be in the bottom but very minute quantity. The majority is lying in my overhead product. You go to your overhead product and over here we need to add the mass fraction of this component. In optimizer of Aspen HYSYS, this is located under the master list. So this is the master component mass flow. If you click this, you can see that we don't need this. If you click on the master component mass fraction, that's what we need. And click on this and we need tetrahydrofuran, the mass fraction, and just add this into your system and click on done. So it has brought that purity into my calculations. Now the bottom production rate is something which is the mass flow of the bottom stream. So this is my bottom product, and now I can select the mass flow here. You can also type in on this box to get the same thing. And now the toluene property, again it will be higher in the bottom, a very minute quantity in the top. So I will take this bottom product and I need to go to the master component mass fraction here. This is my toluene here. Click on add and click on done here. And for the feed flow rate, that will be the mass flow of my feed. Right click on this. This is my feed. And I can also search here mass flow and just add them, and here we go. Now these are black in color because those have been calculated by HYSYS. So one thing you need to keep in mind is we must bring them through the HYSYS rather than we type them ourselves. Why? Because once I will set up the formula for the profit, the HYSYS optimizer will change these values based on the change in your constraint values. So if you have provided your values, it will not change the calculations in the system itself. Now let's enter our cost and price data. So I go back here. My cooling cost is this one. My heating cost is this one here. This is the feed price, and these are the prices for pure toluene. These are the prices for the pure toluene. Just keep in mind the word pure here, because I need to refer you something after I enter these values. Let's take a different color here. Okay, so I'm going to add these values into my spreadsheet of optimizer. So my cooling cost is 0.471 dollar per kilowatt per hour. My heating cost value is 0.737 dollar per kilowatt per hour. The price of my pure THF that I can receive is 0.333, and similarly the price of the pure toluene that I can get as an income, that is equal to 0.136, and the feed cost is 0.05. So once you have all the values set up, now we will calculate our profit based on this equation, which is our objective function. So what we need to do, let's set up the formula here for this. We go here, and this is the variable that we are dealing. It is dealing with D8, so this is present in the D8 cell. So let's start with the first one. The first thing I need to find out is the total toluene selling price. Allow me to explain this so that you will be able to understand this. So let's go back here, and I will make a new sheet. So what I'm looking for, total I'm looking for total toluene selling price. That's what is my objective in finding out the price. Now this will be equals to, that is equal to the price of pure toluene, which will be in terms of right now the value is 0.136 dollars per kg. I will multiply it with the flow rate of this stream. The toluene in my column is coming at the bottom, so that should be your bottom flow rate, and it will be in terms of kilogram per hour. Now if you compare these ones, let's use some different color. These units of kg, that will be cancelled out with the units of the kg. So now we will have the price of the pure toluene, which is 0.136 dollar, and multiplied by my bottom flow rate, whatever it is. Now keep in mind that this price of the toluene, this is for a pure component. What I will do, if I don't have the 100% composition of the toluene, I will just multiply this by the composition of toluene in my system. I should multiply this by the composition of toluene in my system. So the same thing I'm going to apply in spreadsheet of the optimizer. So let's go back, and we will look on this. So we want to include the income because of the toluene and THF. We are doing for the toluene first. So this is my pure toluene price, which is here in cell D6. So that should be equals to D6 multiplied by the bottom product rate, which is available in B5, and it should be multiplied by the purity of the toluene in my system, which is B6. I hope it is clear to you what I'm doing here. And plus, now we need to add what is our total THF selling price. The concept which I explained you here, it remains the same. At this point, what we will do, instead of the toluene, we will take that for THF. The price of the pure THF will come here, and because it is coming in the THF is coming in the top product, overhead product, we will multiply it by the overhead product, and then we will multiply it with the composition of the THF in this system. So we will have plus sign, and this is my price of the pure THF. It is D4. It will be multiplied by overhead production rate, which is B3, and multiplied by the purity, which is B4. So we are done with our income here. Now we need to work on what is the value of our cost here. So we are having feed cost, we are having the heating cost and the cooling cost. So in order to find feed cost, we have this feed cost, which is D7. This is per kilogram. That should be multiplied by your B7 here. This is what will give me the feed cost. Now plus the next is the heating cost. So this is my heating cost, which is in D2. That should be multiplied by, now this heating cost is because of the boiler duty, and it should be multiplied by B2, and plus my cooling cost, which is D1, multiplied by the condenser duty, because the cooling cost is associated with the condenser, and close the parenthesis and hit enter. Now this equation or the mathematical model is what we call as our objective function. If I take you back to my slides here, so this is what was our objective. It is a mathematical model that either needs to be maximized or minimized. So we will see how we maximize this model. Why maximize? Because it is the profit. If it is a cost, we will have to minimize this. So once you enter on this one, it is giving the profit, which is 11.30 kilowatt. Of course, it is in terms of the dollar value. The unit should not be kilowatt. How you can change it? You go here, and there is no dollars units that we can change it. So let's keep it as a unitless. So kilowatt are gone. Now our profit is $11.30 here. In the next step, once you have entered and find out your develop your objective functions, what you can do, you can just close it. But before that, I just want to show you some points here. This my formula is developed in the D8. If you look on your spreadsheet, this is my D8 cell, and these are different parameters that we are using, and these are different connections that we have developed in our spreadsheet. Now what will happen once we run our simulation for optimization? It will change these variable until we have the maximum value of the profit attained. So let's close this and come back to our functions here. Now your cell is the cell which you want to maximize is the profit, and it is available in D8. Yes, you can also check it again. So this is my D8 cell here, as you can see, and I want to maximize this because it's the profit. If it is the cost, you can minimize this. Once you have selected these parameters, you can see that currently I'm getting the profit of $11.30 with the current system. Now let's the simulation here, click on start, and it will solve the optimizer, and it will try to find out the maximum profit value for us. As you can see, it has solved my optimum solution, and according to this I have a profit of $65 and 64 cent available at the maximum. This is the maximum profit that I can achieve. Now in achieving this profit of $65.64, what it has done, if I go to my distillation column, I can go to my monitor, and I can see that these are the new composition values that it has calculated. Our the only change that it's making is it is subtracting 0.0001 for THF, and it is subtracting 0.0004 from toluene purity, and based on these new values it is suggesting that our profit can be $65. So this is how you do the optimization in HYSYS. The procedure which I mentioned you is the same for every equipment that you're using. One thing I just want to mention, that this spreadsheet that is available in the model palette, if I bring it here into my system, this spreadsheet is not the same as your spreadsheet of the optimizer, because this is coming through an optimizer spreadsheet. So both of them are different. So let me delete this. What I would suggest you, if you go to this workbook here, now this is the book which is the optimization of chemical processes. I will make its chapters available. Please work on chapter 1, 2 and 3. You will be able to understand how we formulate the objective function, and there are some examples here that you can also try in HYSYS. And if you have any questions, you are more than welcome to email me. I will be happy to answer them, or you can see me in my office. I hope this helps, and thank you very much.